Safety engineering used to be about fixing broken things, severed wires, or microchip failures. This split screen shows the shift. On the left, a traditional hardware short. On the right, a system accurately processing its environment while its driver is completely distracted. This right-hand scenario is the new crisis in vehicle automation. For years, the industry relied on the ISO 26262 standard to mitigate electrical and electronic failures. It is highly effective at ensuring physical components and software code operate according to their technical specifications. However, modern accidents frequently occur when systems operate exactly as programmed. These hazards emerge from the functional limitations of sensors and the inevitable gaps in how humans interact with them. ISO 21448, known as SOTIF, or the safety of the intended functionality, was developed to address these specific risks. SOTIF requires manufacturers to engineer against reasonably foreseeable misuse. Success now depends on modeling human unpredictability and building technical defenses to contain it. Human behavior is no longer an external variable. It is a core functional safety parameter. The vehicle must be designed to actively supervise the driver's attention. This matrix separates human error into two structural categories. Direct misuse represents an active choice to break rules, while indirect misuse involves a passive failure to maintain control. Direct misuse occurs when a user activates a system outside its specified operational design domain, like using highway cruise control in a dense urban construction zone. If the car technically allows this, it is classified as an insufficiency of the system's specification. Indirect misuse is more difficult to detect. It occurs when a driver fails to regain control after a system reaches a functional limit, often because they have stopped acting as an effective supervisor. The Yerkes-Dodson law plots psychological arousal against task performance. When a system performs perfectly for long periods, it removes engaging stimuli. The driver's arousal slides to the far left, resulting in a state of dangerously low performance and high reaction latency. This automation complacency is a biological reality rather than a character flaw. High-reliability systems naturally erode situational awareness by training the brain to expect no need for intervention. Automotive engineering must now stabilize the human supervisor as aggressively as it stabilizes the vehicle itself. These psychological theories are validated by the data found in National Transportation Safety Board collision reports. These investigations provide a roadmap of how faultless engineering can still result in a fatal crash. Consider the Uber ATG crash in Tempe, Arizona. NTSB investigators found the safety driver had been streaming a television show on their phone for several minutes leading up to the fatal impact. This crash illustrates SOTIF root cause 3, learned carelessness. The system's reliable performance over hundreds of hours had conditioned the human to assume their supervision was no longer necessary. In another collision involving a Tesla Model X, the NTSB determined the driver was actively playing a smartphone game while the vehicle was in motion. This crash exposed a specific failure in root cause 5, an incorrect assumption regarding how a user would interact with the safety sensors. The car used a torque-based steering sensor, which misinterpreted the weight of a resting hand as active supervision. Under SOTIF, relying on a physical force as a proxy for visual attention is an engineering insufficiency. Engineering a system that operates perfectly in isolation is lethal if that design assumes the human will always act with idealized focus. Safety design must also address the boundary between misuse and abuse. Abuse involves the deliberate defeat of safety protocols, such as using weights to trick sensors, or, as seen here, sleeping behind the wheel. Regulatory standards now dictate that if an abuse tactic is widely documented on social media, it becomes reasonably foreseeable. At that point, the manufacturer is responsible for designing a technical countermeasure. ISO 21448 Table 5 provides the toolkit for identifying these specific scenarios before they result in a crash. Method A involves internet media analysis. Engineers scrape platforms like YouTube and Reddit for hacks or defeat devices. A viral video showing how to trick a torque sensor creates a new functional requirement for the vehicle's design team. Method F uses human behavior modeling and cognitive architectures to calculate real-world response times. These models predict exactly how long a distracted driver takes to process a takeover request and physically resume control. By setting the boundary of liability at what is reasonably foreseeable, SOTIF removes the ability of manufacturers to blame user error for predictable design flaws. Mitigating these risks requires a complete hardware transition. For 2025, the primary safety focus is moving from the steering wheel to the cabin interior. Capacitive hands-on detection is replacing torque sensors. By measuring electrical capacitance instead of physical force, the system requires actual skin contact. This prevents users from using inanimate objects to trick the car. Manufacturers are also deploying DMS 2.0, utilizing 60 GHz radar and infrared cameras to monitor the driver's biological state. These systems track days and respiration to identify cognitive load. The car can detect if a driver has physically looked at a hazard but failed to cognitively process it, providing a warning before a collision becomes inevitable. Computing the driver's internal readiness is now as vital to safety as mapping the road. If the car detects a non-responsive driver, it initiates a minimum risk maneuver. It autonomously activates its hazards, slows down, and moves to a safe stop on the shoulder or within the lane. This highlights the automation paradox. As systems become more reliable, the design of the interface between the machine and the human becomes the most critical point of failure. SOTIF confirms that the ultimate challenge of autonomous driving is the mathematical containment of human nature.